more about singularities. So, what did we learn last time? So we say F has a pole at Z0 if 1 over f of z has an isolated 0 at Z0. In fact, all zeros are isolated, so I'm not going to bother to say that anymore. So has a 0 at Z0, yeah? And so that means that this function, 1 over f of z, can be written of the form z minus Z0 to the n, g of z, where g is holomorphic, in some little ball around Z0. For some bigger than 0. Emphasize this is often a very small one. And just unwrapping what this says, that means that f of z looks like this. It looks like 1 over z minus Z0, and let's write this function g of z like this. And 1 over g of z is a perfectly nice holomorphic function because it's non-zero at Z0. Right, this is holomorphic for some, and g of Z0 is not equal to 0. So for small enough ball, because it's continuous, we can assume that g of z is non-zero everywhere inside this ball, so 1 over g of z perfectly makes sense. It's a differentiable function. This is a nice holomorphic function. Yeah, this guy's a perfectly nice holomorphic function. So what that means is that, and I dropped the n here. What that means is that this part is behaving in a very predictable way, right? It's holomorphic. Since g of Z0 is non-zero, as we approach Z0, this tends to more to the value of 1 over g of Z0. Yeah. So the actual blow-up behavior is like this. The actual blow-up behavior is defined by this. Yeah. Yeah. So near Z0, f of z blows up like z minus Z0 to the minus n, and just this thing here, which is just some particular complex number. Yeah. So it's got a singularity, but it's an incredibly regular singularity. Its singularity is very manageable, and n is called the order. So n is called the order of the pole. And if n is 1, we're going to call this a simple pole. So if n equals 1, this is a simple pole. And we also learned that if we expand out this function 1 over z as a Taylor expansion, so 1 over g of z is, say, the sum k equals 0 to infinity bk z minus Z0 to the k, because it's holomorphic, it's nice, so in some small region we do have this expansion. This is what we learned. Then, writing this out, so I'm not going to repeat all the details, but it's kind of trivial. What we find is we have this. We have the sum from k equals 0 to n of a to the minus n z minus Z0 to the minus n, like this. And this is the part that produces the singularity. And this thing right here, sum from k is equal to 0 to infinity of a k z minus z0 to the k. This part is the nice holomorphic part. And the way we found that is that we just put this into this, and then take this z to the minus n through, right? And then this part will be all the part where we have negative powers of z minus z0, yeah? And then this part is everything else, yeah? So this part right here is perfectly nice. This thing is holomorphic. This part is what we call the principal part. And this is the part where the singularities occur. And at the end of yesterday, at the end of last class, I said some stuff about the first non-zero term of this expansion is where we have the actual blow-up occurring. But the way this thing is being constructed, the first non-zero term has to be a to the minus n, because we have the blow-up is of order z minus z0 to the n. Yeah? So we actually know that a to the minus n is non-zero. See what I mean? Otherwise it wouldn't blow up as fast as this. Everybody with me? Okay, cool. So what I also said was that that while the most significant, it's blowing up at the rate of z minus z0 to the minus n. Damn it. While it's blowing up at the rate of z minus z0 to the minus n, that's not the most significant term. So it actually turns out that the most significant term, the most important part of the singularity, is not this part. And that comes down to this following very nice little calculation, which you actually did for homework and kind of was implicit in the exam. And it's the following. So let's call this a lemma. If we take the integral around the boundary of the ball, when I don't put anything here, it means the ball is around 0. Cool. So boundary of the ball of radius r of 1 over z to the n dz, then this thing is equal to either 2 pi I if n is equal to 1, and 0 if n is not equal to 1. Okay, and this is, this can be seen in multiple ways, but it's also just an elementary calculation. So I'm going to ask you in a minute what theorems also tell us that this is the case. But for the time being, let's just calculate it. Let's create a parameterization of the boundary of the ball of radius r and see what happens. So if we let z of t be just e to the it, that's a nice parameterization of the ball. Yeah, z prime of t is equal to I r e to the it, and then let's see what happens when we do this integral. So I'm going to integrate from 0 to 2 pi, 1 over this thing, and then I r e to the it dt, just using the definition of contour integration. So then we have a fair bit of cancellations here, right? So what are we going to have? We're going to have, let's pull out the I straight away, and then we're going to have, let's actually pull out also the R, because it's not involved in the integration itself. So let's pull out the I, and then we have R to the 1 minus n here. That looks really bad. Do that again. So I to the R to the 1 minus n. Looks slightly better. And then what do we have? Then we have just e to the it to the power of 1 minus n. So 1 minus n like this. dt. This is what we have. Yeah? Everybody happy? Yeah? Let's continue it down here. So then what's this? This is equal to I r to the 1 minus n. And if we just expand this out, we know what e to the I whatever is. So it's equal to cosine of it 1 minus n plus, oops, not it, cosine to the t times 1 minus n plus I sine to the t times 1 minus n dt. Yeah? And if n is not equal to 1, then this thing is just some function which is periodic from 0 to 2 pi. Yeah? If n is any number except 1, then this thing is just a nice periodic function from 0 to 2 pi. And when we integrate it from 0 to 2 pi, since the antiderivative is periodic, it just is 0. And the same is true for this. Do you see what I mean, people? Yeah? Everybody give me a thumbs up, or if you see what I mean. Okay. Okay, cool. So then everything here just vanishes. So this is just 0 if n is not equal to 1. And on the other hand, if it is equal to 1, then what happens? Well, then this thing is 0. This thing is cosine of 0, which is 1, right? And this thing is just sine of 0, which is 0. So if n is equal to 1, then let's call this thing star. Then what is star? It is just equal to well, this part here is just going to be I times r to the 0, so it's just going to be I. And then this thing here is just 1, and then plus 0 times I. So it's just 2 pi I, and that's it. So that's our claim right here. That's our claim right here. Yeah? Cool. All right, so why did I take you through this? Well, let's see what happens if we have a function with a pole. Yeah? If we have a function with a pole, then our theorem is that we can write it in this form like this. Yeah? And then let's take our function with a pole and let's integrate a little circle around z0 itself. Okay? We make the circle small enough so that it's within the radius for which this representation holds true. Yeah? Okay. Now I'm going to raise the board. I want you people to think about what will be the integral of a function f, which has a pole and therefore is representable this way, when we integrate it around the little ball of a small radius around z0. Yeah? Think about that while I raise the board, and then tell me about it when we're done. Okay, so if we have a pole at z0, and so we have this representation locally around z0, so the small ball, the sum from k is equal to 1 to n of a to the minus k, z to the minus z0 to the minus k, and then the next part is holomorphic, so I'm just going to write, okay, let me write it as an expansion to begin with. The sum from k is equal to 0 to infinity ak z minus z0 to the k. And so let's draw a picture. So we have our domain. We have some point here where f actually has a pole, and we're taking a little tiny radius around this thing. This is z0. Tell me about what this thing will be. So if we integrate around the boundary of the ball of radius r around z0 of f of z dz, tell me about this. Don't have to tell me everything, but tell me what you know, given that we have this representation. In what ways do we have a simplification of this thing? Perfect, yeah. Perfect, yeah. So we can just break this up into this thing, the sum k equals 1 to n. Let's take out the coefficient a to the minus k. Why not? Integrate around this thing. Z minus z0 to the minus k dz plus this thing here. This part here. Yeah, and exactly as Jaime said, this thing here, if we do a change of variables and rescale it so that z0 is not rescale but reposition it so that z0 is 0, then it's exactly the integration we had before, right? Or you don't even have to do that. If you just create your parameterization, then it's exactly the same parameterization, except it's z of t is r e to the it plus z0, and the same thing happens, same calculation happens, right? So we know that everything here will cancel except the term when k is equal to 1, yeah? And when we have k equals 1, then this integral just becomes 2 pi I, yeah? And this thing is just holomorphic. It's just holomorphic. It's a little ball where it's holomorphic, so just by Cauchy's theorem, this thing is equal to 0. Yeah? Or Gauss-Stett's theorem, I should say, in this case. Yeah? So the only thing that survives from here is just 2 pi I a to the minus 1. Yeah? Which is pretty extraordinary. So we have this integral around this little ball, and the only thing we have to care about is just what the coefficient a to the minus 1 is. And it's extraordinary because if instead of integrating around a little ball, suppose we integrated around a closed curve, which just contained one pole, and that one pole is z0. Yeah? Yeah? Then I claim that the integral around this closed curve gamma will also still just be this thing. Now tell me why. Let me write that down and you give me an explanation. Suppose gamma is a closed curve, or a simple closed curve, which contains only one zero. Sorry, which contains only one pole. Then I claim that the integral around gamma of f of z dz is still 2 pi I a to the minus 1. Tell me why. This was something, this is some principle that we've used, and on reading some of your homeworks and also your exams, not all of you are that comfortable with this. This is one of the basic things that we use to simplify life when we do contour integrals. And we've used it a fair number of times. So what thing can we do to make our life easier when we have a contour integral? Remember how we proved Cauchy's integral formula? Yeah? We had some point in the center of this closed curve, which we're integrating around, right? But we don't actually want to deal with that contour. We wanted to deal with another one, yeah? Yeah? We wanted to deal with a little ball, the boundary of a little ball around that particular point. And we're able to reduce it to that situation, right? Because what did we do? How do we do it? What do we use? We used the keyhole contour, and how did it work? Why were we allowed? So let's blow up this thing here. Let's blow it up to this scale. So we have z0 here, and this is some closed curve, gamma. Yeah? Just like in the case when we had Cauchy's integral formula, we're able to reduce the integral around this closed curve to the integral around a little ball, like this. Yeah? And as you say, we use the keyhole contour. Yeah? So a keyhole contour is when we make a little break like this, and then go down, up. So if we put the parameterization, we go around like this. Always anti-clockwise. Yeah. And how did this work? How did we reduce the integral around gamma to the integral around the boundary of the ball? What was the theorem we used there? So one of the reasons I emphasize to you that I want you to understand and study and be very able to recall the proofs is that the proofs have these key methods that are used over and over again. And if you account with these key methods, then many of the theorems just fall out rather naturally, and this is one of them. So think about how we did this. How did we reduce the integral around the outer contour gamma to the inner one around the boundary of the ball? So Jamie's right, Hamid's right, that we had the cancellation here on this little hole part connecting them, yeah? So ultimately that thing becomes unimportant. So that when we take the limit of this thing as the hole goes down to 0, it just becomes the integral around this thing. But if we look at this guy here is actually going clockwise around the circle, yeah? So then as we let the whole thickness get thinner and thinner in the limit, this integral just becomes the proper anti-clockwise integral around the outer curve minus the anti-clockwise integral around the inner circle. Yeah? And what we want to do is say the integral around the outer curve is equal to the integral around the inner circle, which would mean that entire expression is 0. Yeah? So why do we know that entire expression is 0? Think about our context. We have a function f. It has only one pole and has no other singularities. Just got one pole here at z0. Yeah? So let's call this keyhole contour here. Let's call this keyhole contour pi of delta, where delta is the thickness of the little hallway here. Yeah? So let's call this thing pi of delta. Tell me what this is. What is the integral of pi of delta f of z dz? Why is it 0? Yeah, Cauchy-Gorstadt's theorem, yeah? Because this thing here, yeah, is contained within what I called a dyadic good region, right? Where we have an actual antiderivative. Yeah? That's exactly how we proved Cauchy's integral formula. Cauchy's integral formula, we had some expression like this, f of zeta minus z, which was nicely holomorphic except at z itself. So we did a keyhole excluding the z, yeah? And then we had that the integral around this keyhole contour was equal to 0 because this function has a nice primitive on this dyadic good set that contains this keyhole contour in its interior, yeah? Is that coming back to you? Give me a thumbs up if it comes back to you. Okay, good. So what this is the principle of deformation of curves, that if we have some complicated curve, yeah, but we can create some keyhole contour to reduce it down to some simpler curve just by having that the keyhole contour has its interior and its closure on a set where the function is nicely holomorphic. If that's the case, then we can just apply the fact that we have a primitive and this thing has to be equal to 0 for every thickness delta of the hallway. Yeah, so let's put it somewhere here. So remember, we proved there is a primitive whenever you have a circle, just by doing this stuff, yeah? Yeah, defining a function. If this is z, we define a function f of z to be the integral. Let's call this thing gamma of z, this L-shaped thing that goes from 0 to z, yeah? So this thing is the integral of gamma of z of f of zeta of d zeta, yeah? And then we proved that f prime of z is equal to little f, and therefore it has an antiderivative, and therefore every closed curve is equal to 0 when we integrate it around this thing. And the fact that we can do this uses Cauchy's theorem because this thing is only well defined because of Cauchy's theorem. Yeah? That's the order of events. Now, for any dyadic good, then a dyadic good is when we take a collection, we break up the complex plane into these little squares, and it's dyadic good if it is if we just consider a collection of these squares, whatever shape they are, like this. So they're defined, so we index the squares with some integers, and the collection of squares is indexed by some I contained within natural number, the integers like this, okay? So a dyadic good, D good, is the union of all these K belonging to this index set of these squares, let's call them QK, yeah? And it's dyadic good if, okay, all right, let me just finish the sentence in case it's useful to anybody else. So dyadic good means that the complement of all of these guys, so all the guys which are not inside our dyadic good, have to form a connected unbounded set. Okay, so in particular, dyadic good can't contain a whole. This is just a rough way to say you can't contain a whole, because later you'll learn we have to be a bit precise when we mean it can't contain a whole. So when it's dyadic good, then we can do the same argument because this thing is still well defined in a dyadic good domain. Everything works in the same way just by breaking up any path into little triangles where they all cancel. Okay, and that was one of your homework exercises, to show that this theorem holds true in a dyadic good. Yeah, it's kind of a lengthy and technical thing to show, but it is just following from a simple way that no matter what dyadic good set you have, if this is dyadic good, you can still create a path up to it, and any other path you create to your point will define exactly the same function, because you break it up into rectangles or triangles where everything cancels. I'm glad you asked this question, because it gives me a chance to go over some fundamental things. Is everybody happy with that? Yeah? Cool. All right. So back to our story here. Let me erase this thing. Since our keyhole contour is contained within a dyadic good set by just making these squares small enough, therefore we have a primitive on it, and therefore the integral around the closed curve is 0. So we have that this thing is 0. Yeah? Yeah. And the key point is indeed that on this set it's holomorphic, because we've excluded the one point where it's not. Cool. All right. So we have that this is equal to 0. Yeah. This is equal to 0. And if we let delta go down to 0, then exactly as we've seen before, the sides of the hallway will cancel each other out. Yeah. So this is true for all delta bigger than 0. So taking the limit as delta goes to 0 of this thing, of z dz, we did this somewhat carefully before. We saw that this thing cancelled. This is equal to the integral around the outer contour, this thing, minus the integral around the boundary of the ball of radius z0. Huh? Like this. Yeah. So in particular, the integral around the outer contour just reduces down to the integral around the boundary of the ball, and we can make the ball as small as we like. Yeah. And we call this the principle of deformation of curves. That whenever you have a curve, you can just reposition it around whatever interesting thing is happening that you actually want to understand. Yeah? And that makes these calculations very much simpler. And that's how we're able to prove Cauchy's integral formula, because this expression is hard to understand except when we go on a very small ball, and then it becomes rather easy to understand just by differentiability. Yeah? Because by differentiability, we know what f looks like. It looks like its tangent plus some higher order terms. And then we can calculate this expression rather easily. Yeah? Cool. All right. So whenever you have a homework problem or any kind of problem involving doing some integration, think about deforming the curve to a more convenient curve by creating a keyhole contour where on the interior of the keyhole contour, your function is actually holomorphic on the interior and on the boundary. Yeah, and that'll save you some work. All right, and in this particular case, I claim that we can actually reduce the integral of this closed curve here down to this thing. It follows exactly from this calculation, right? So we know that this thing's equal to 0. So the integral around this contour f of z dz is just the integral around the little small ball. And that thing is indeed what we've just calculated, 2 pi I a to the minus 1. So this is, again, this is super powerful. This holds true for any closed curve containing Z0, which is to me was very, very striking and very almost hard to believe when I first saw it, because obviously you have completely different curves. I mean, it's a totally different situation in real analysis of real valued functions from the real line, because if you change your domain, you obviously get your completely different integral. Yeah, integrate over a different set, you get a completely different integral most of the time, unless the function is identically 0. Yeah. So here we have a non-trivial function, but we can have any closed curve we like, and we get exactly the same answer out. Exactly the same answer out. It's quite a shocking result in lots of ways. You know? So yeah, this is the start of so-called residue calculus, which allows us to explicitly calculate many integrals by this principle. And this principle is actually rather simple. So shocking though this result is, the principle is rather simple. We haven't actually had to prove very much. All we've proven is this thing, which is just elementary, right? This doesn't take long to prove. Do it for yourself. It'll take less than 2 minutes, right? Just from the fact of the definition of a pole. Yeah, this is just trivial. Well, not trivial, but this is rather quick. Yeah. And then the second thing we've proven is that if we integrate 1 over z to the n, yeah, it's either equal to 0 if n is not equal to minus 1, if n is not equal to 1, or it's equal to 2 pi I. That's the only other thing we proved, and that's an elementary calculation too. Those two things together imply this, plus the keyhole contour principle, plus the deformation of curves principle. Yeah? Imply this strikingly strong result. Another thing to say, I didn't fudge anything here. I didn't do any funny swapping of limits underneath integral signs, because when I do this, here I have just a nice finite thing. It's just a finite collection of terms. Yeah? So I can indeed break it up into the sum. And this thing here, which is the infinite sum, I'm just considering as a holomorphic function. I'm not passing integral through. I'm just applying the fact that this thing is equal to 0 just by Cauchy-Gorstadt theorem. Yeah? So this is completely rigorous. I'm not fudging any technical details. Yeah? So this remarkable result really does follow very, very easily. It's a very, very easy result. All right. Now, tell me what you expect to happen when we have a more complicated situation. What about this? What about if we have numerous poles, say Z0, Z1, Z2, Z3, Z4. All of these guys are poles. Yes, I know what you're saying, but it's not. It's the same keyhole, but we're going to. Yeah, I know exactly what you're saying. It's the same contour, but we have multiple keyholes going around these things. So we go down, put a little thing like this, yeah, and then something like this, and then something like this. Did this wrong. Something like this, and then a guy like this. Yeah, and that is how we're going to break up this integral. And then the same principle will apply, right? The same principle will apply. So, did I do this wrong? Yeah, I did it wrong. Around this way. and then like this way. All right, so tell me what will happen then if we have, let's not make it 4, let's make it n. Suppose not n, let's make it p. We have p poles inside of our contour here. What will this integral around this curve reduce down to in that case? Yeah. I see exactly what you're thinking. I understand why you hesitate for a second. So actually, I don't like the index p anymore. Changed my mind, calling it m. I've learned recently that many foreign mathematicians call pi p. And some French guy justified this to me, saying that that's the Greek pronunciation. So that was interesting. That leads to confusion with the letter. So let's call it m. Okay, so if we do this, then sure enough, it's going to reduce down to the integral of around these m individual little balls around the singularities, yeah? So we're going to take the sum from k equals 1 up to m around the integral. And on each one of these guys, we're going to take some radius which is small enough so that it's within the radius for which we have this kind of expansion, and therefore we have that the integral around this boundary of the ball turns out just to be this very simple expression given by 2 pi a to the minus 1, but there's a caveat. So let me write this and then tell me how I should write the next thing. So since they're finitely many, we can choose the same r, which is small enough for all of them. That thing won't be a problem. dz, so just the contour principle, well, definition of curve principle, I should say. And then this thing reduces down into something simpler. But tell me what I should write here. Tell me what I should write here. I mean, you said it before. Well, you said, tell me what you think I should write here. Perfect. That's exactly the caveat. We have to think a little bit carefully because each one of these things here, we can calculate depending on the expansion we make around this pole. Right? We made the expansion around the pole in this thing here. So this is only true in a small radius around Z0. Yeah? And the coefficients here depend on the expansion. Yeah? So this coefficients here depend on the fact we're expanding our function around Z0. And around Z1, we'd have a different expansion with different coefficients. Yeah? Yeah? Key point. So it might be tempting to write a to the minus 1, but as you hesitated because you're aware that for different points, then we're going to have a different a to the minus 1. Yeah? So we need a better notation for this a to the minus 1 term. Yeah? We need a better notation, and that motivates the concept of residue. So here I don't have a good thing to write because I don't know how to write a to the minus 1 in a way that indicates it's around each one of these things. I haven't got a notation for it yet. So therefore we need a notation for it, which is the concept of residue. So definition. The residue of f at pole, so I'm going to call it Z0, but it's not this Z0, it's any Z0, which we write like this, res Z0 of f is equal to a to the minus 1, where f has the expansion f of z is equal to the sum k is equal to 1 to n, a to the minus k, z minus z0 to the minus k. And now I'm just going to write h for the holomorphic part like this. Okay. So this definition is convenient for us because, or it's useful for us because it specifies that we're talking about the a to the minus 1 at this particular point where we have the pole. Yeah? And that's what we need in order to write something meaningful here. So we write this. We write the residue of at zk of f. And that's all that residue means. Yeah. So when I first saw it a long time ago, I thought this is a kind of complicated expression, but no, it's not. It is just that we want some notation that allows us to specify what a to the minus 1 coefficient we're talking about when we have a bunch of separate different poles. Cool. So that's an even more extraordinary result. So it means that if we have a function that just has a collection of poles inside our contour, then all we need to do is this finite addition of just what the residues are at the individual poles. And that is the so-called residue theorem. That's the residue theorem. And that's one of the most striking and deepest theorems in this subject. And it's one that has enormous power, as we're about to see. Okay, let me raise the board. Okay, so let's write what we've learned as the theorem. Theorem. Suppose f from omega into c is such that for simple closed curve gamma, we have that f has only finitely many singularities Z1, Z2, up to Zm. So int is the interior of the simple closed curve, and f is hollow on the closure of the interior of the simple closed curve. Take away these finitely many points. Which means it's holomorphic on some open set that contains the closure of the interior, subtract this finitely many points. Then integral around this thing is the sum from k equals 1 up to m of 2 pi I, the residue at zk of f. Cool. So that means that in order to calculate a whole wide, massive class of integrals, all we need to do is to calculate residues. Yeah? We need to calculate residues. Yeah? And this is almost as good as it gets, because if there is no singularities inside the closed curve, then as you know, the integral is 0. So if we get anything non-trivial at all, we're going to have some singularities. Yeah? Yeah? The specification is that we want finitely many of them, and we want them to be poles. We don't want them to be essential singularities. All right, cool. So we want to calculate residues. So we want to be able to calculate residues. Now, in the case when we have a simple pole, it's rather easy. So suppose F has a simple pole at z0. Then what does that mean? That means z is equal to a to the minus 1, z minus z0 to the minus 1 plus some holomorphic function like this. Yeah? That's exactly what simple pole is. The order of the pole is 1, so therefore that's the only term in the principal part. Then, if we just look at this, let's take the limit as z goes to z0 of z minus z0 times f of z. What happens to this? This is the limit as z goes to z0 of, just multiply this thing through, of just a to the minus 1 plus z minus z0 h of z. H is a perfectly nice holomorphic function. It has a limit as z goes to z0. So this part here will just vanish. So that's just equal to just a to the minus 1, like this. Yeah? So this thing gives us the residue in the case we have a simple pole. In a more general case, we have to work a bit harder. So theorem. Suppose F has a pole of order n at z0. Then we're going to get the formula by taking z minus z0 to the n and then multiplying this by a function like this. And then we want to differentiate this n minus 1 times. And when we do that, we're going to have a bunch of factorial expressions which we want to divide through. So we're going to divide by n minus 1 factorial. And that thing will be the residue of our function at f of z0. Oh. So Stein's notation is to put the z0 here. I'm a bit tempted to do this because I feel like the z0 is pretty small for you to see if I put it as a subscript. So maybe I'm going to write this. Maybe I'm going to write it like this. Do you prefer it like this with this notation, or are you happy with this? Give me a thumbs up if you prefer this notation. All right. Just two of you. So it seems you don't mind. All right, so we'll continue with the Stein notation. All right, so this is what we have. So why is this true? This is a calculation. So if we have that it has a pole of order m, what does that mean? That means f of z is of this form, the sum from k equals 1 up to n, a to the minus k, z minus z0 to the minus k, and then plus the holomorphic part that we don't have to worry about. So when we multiply this thing by z minus z0 to the m, to the n, I should say, what happens? Then we get just this thing, k equals 1 to n, a to the minus k, z minus z0 to the n minus k, and then this part here, which is harmless for us, h of z. Yeah, let's write out some of these terms just to make this clearer for us. What do we have? So we have a to the minus n, and then we're going to have z minus z0 now let's start it from a to the minus 1. So we have a to the minus 1, and then we have z minus z0 n to the minus 1, and then we have a to the minus 2, z minus z0, n to the minus 2, and then so on. When we have k is n minus 1, we have a to the n minus 1, and then z minus z0 to the n minus 1, so this is just to the power 1, and then the final thing is a to the minus n, and that's just going to be n minus n, so that's just 1. N to the minus n, and then this stuff here, which is z0 to the n h to the z. Yeah? Just writing out what this is. So let's think what happens when we differentiate n minus 1 times. So if we differentiate this thing n minus 1 times, right, then every time we differentiate it, we're going to put down the power, put it in front, right? And then if we differentiate n minus n times, what happens to it in the end? What does it turn into? Let me put it somewhere. So we're going to differentiate this thing, z minus z0 to the n minus 1. What is it going to turn into? Yeah, just n minus 1 factorial. Yeah? Because every time we differentiate it, we put this number down in front, we lower the power. Yeah? We do this n minus 1 times, it's going to be n minus 1 minus n minus 1, which would be 0. Yeah? So we end up with this thing. Are you all with me here? Give me a thumbs up if you are with me. Okay, cool. All right, what happens when we differentiate this thing n minus 1 times? We get 0. Yeah, we get 0. What happens if we differentiate the next term here? 0 again, right? Differentiate this thing n minus 1 times. 0 again. This thing, of course, 0 is a constant, right? So then we just have to think about what happens when we differentiate this thing n minus 1 times. Yeah? So let me try and put it on the bottom here. So if we differentiate d n minus 1, say that again. If we differentiate n minus 1 times this expression here, in order for our theorem to be true, this thing can't be a problem when we take the limit as z goes to z0. I hope I did put that. I didn't put that. Sorry. Didn't put the key thing. So this thing is differentiated as we take the limit as z goes to z0. So it's the analog of this result here. It's the higher dimensional analog of this result here. So this thing right here, if it's true, then we should not have this guy playing a role, because we've seen that the only thing that is remaining when we differentiate all of these guys is just the thing that we want, the a minus 1 coefficient and then n factorial. Yeah? You see what I mean? Yeah? So in order for this theorem to be true, what we would like to have is that this guy here doesn't mess things up for us. Yeah? Because if we knew this thing was 0, then our theorem would be true, because that's what we've just seen. Yeah? So backward engineering what we want, we'd like this thing not to mess things up for us. And I claim that it is the case that it will not mess things up for us. And it just follows from looking at the expression. So look at this expression. We don't need to understand too much about this, except that when we take the limit as z goes to z0, that this thing will go to 0. That's all we need for this thing. Yeah? We need this guy to die quietly. So what about this guy allows us to conclude it dies quietly when we take z goes to z0? Perfect. Perfect. Yeah. Yeah. So if we use the product rule over and over again, so let's just differentiate once. We hit this guy, we'll reduce the power by 1, leave that guy alone, then leave that guy alone and hit this guy. Yeah. And that expression still has a factor of z minus z0 to the n minus 1. Yeah. Yeah. So we would now be differentiating n minus 2 times an expression with z minus z0 to the n minus 1. Yeah? And then we just keep doing that. Yeah? We just keep doing that. And every time we do it, we find that we still have a power left as we still, let me say that better. Right now we're differentiating n minus 1 n times, and we have a factor of z minus z0 to the n. And every time we do a differentiation, we're still going to be differentiating a certain number of times, but we're going to have a factor of z minus z0 to that number of times plus 1. Yeah? That's what will happen every single time. So that when we go all the way through this entire procedure and differentiate all n minus 1 times, we're still going to have a factor of z minus z0 to the power 1. In all of the expressions, in all the terms. It'll spread out like a massive, messy thing, but every single term will have at least the power of z minus z0 to the power 1 in front of it. Yeah? So that when we take the limit as z goes to z0, this entire guy will just vanish. Yeah? This entire guy. So just summarizing that, this expression will be of the form z minus z0 plus some other thing. Let's call it g of z. For some g, yeah? Well, this is a nice holomorphic function, whatever. We don't care about it, yeah? So, putting it up here, so the limit as z goes to z0 of n minus 1 derivatives of our expression here. It's really badly written. Of z minus z0 to the n times h of z. This is, sorry for this terrible board management. Is equal to 0. Yeah, that's what we have. That's what we have. Yeah? So sure enough, this guy dies quietly. It isn't a problem for us. When we take the limit as z goes to z0 of this entire expression, yeah, all we're going to get out is just a to the minus 1, because we know that the only survivor of the differentiation of this part is just a to the minus 1 times n minus 1 factorial. Yeah? Yeah? And everything else, everything else just vanishes. And then when we take the limit as z goes to z0, this guy just is not a problem either. Or this guy differentiated n minus 1 times is not a problem either. By this, yeah? Yeah? So then all we get in the end is just n minus 1 factorial times a to the minus 1. So we divide by n minus 1 factorial and we get exactly the residue. Okay, cool. All right, so this is a complicated looking formula. And the way to do this is not to memorize the formula. Memorization is strictly forbidden. Some of you, probably all of you, have very good memories. Some people have outstanding memories, and they go very far being able to recapture the form of formulae, and they get all the way to graduate level. But that is not what you want to do. Switch off your memorization abilities in this course, or in any course actually. What you want to do is to backwards engineer this thing. You want to backwards engineer it from what you know about how it works. How does it work? We have this thing here. Yeah? We want to extract out the n minus 1 coefficient. Yeah? So the natural thing to do is to multiply by z to the z minus z0 to the n. Yeah? Because then that produces something like this, and then we differentiate n minus 1 times. We're going to kill a whole bunch of stuff. In fact, we kill everything when we take the limit as z goes to z0. So do not memorize this. Do not memorize this. The way to know this is to take a piece of paper and try and work out the formula for yourself, just from the representation, just from some vague memory. Okay, this is the only thing you're allowed to remember. The only thing you're allowed to remember is that you're going to take the expansion for f, and you're going to multiply it by z minus z0 to the n, and then you're going to do some differentiation. That's all you're allowed to remember. Yeah? So when you revise for this topic, just take a piece of paper, and with the fact that you have the expansion, which is easy, you should know the expansion at this point, and the memory that you're going to multiply by z minus z0 to the n, and you're going to do some differentiation, work out the formula. Work out the formula. And once you've worked out the formula a couple of times, you will not have any problem with the formula, because it will seem natural to you. But just watching me, it might seem natural, but it won't seem nearly as natural as it will be if you actually work it out yourself. And this is what you have to do. This is, as I said before, that since you're applying to enter research, you're going to have to learn mathematics at a deeper level than you've learned previously. You're going to have to absorb the machinery, the techniques of your research field in a very fundamental way. Not enough to know the statements, not enough to verify the proof and believe it's true. You're going to have to just have the essence of the theorem inside you, and just be able to recapture the main techniques to prove it. You're going to have to learn things at that level to make any real progress in anything, in any area of research. And we start learning that, we start this process of learning things that deeply in this very nice, very technically clean subject, where the ideas are very natural and there aren't many technicalities. This is the place where you can do that. And it might be a higher bar than you've previously had to do. You might think it's very hard. You might even think it's not something you can do. And I promise you, you're wrong. You can do this. You can do this. You are able to learn this entire course, have it in your head, be stranded on a desert island and rewrite the entire course from your knowledge of the basic principles of this subject and your basic memory of what the theorems say. You can prove everything and recapture it if you get that level of understanding, and you're all able to do that if you do the stuff I say, if you practice working out the theorems in the way I said. So that is what I'm going to be testing on you. That is what I want you to get to the level at. And if you haven't been doing that, then start doing that. Start doing that. Literally do what I say. Just take a piece of paper. Just use the fact that you're allowed to remember that you multiply by z minus z0 to the n, and you're going to do some differentiation and work out the formula. Yeah? Spend 15 minutes doing that, and you'll find you'll get the same thing. This is not hard. You're able to do this. Okay, we've got 10 more minutes. Let's use this. Okay, so let's calculate this following integral. Maybe we don't get. Okay, let's see how far we get. Let's try and calculate this thing. Okay, using the residue theorem that we've learned. Okay, now when I said at the start of the course that one of the really striking and exciting things for 18th, 19th century mathematicians was that this complex world allows us to answer questions in the real world, what we can't answer, or they couldn't answer beforehand. In fact, still can't answer without these techniques, and that's really strange. That was really striking because the real world doesn't contain complex numbers, but we learn things about the actual world of real quantities from doing things in the complex plane, from this theorem of the residue theorem. This is not an example. This guy we can calculate. Yeah, we can calculate. How would we calculate this if we were doing calculus, if this was a calculus exercise? Yeah, the antiderivative of 1 over 1 plus x squared is arctangent. This thing we can actually calculate. Yeah, so we actually know the answer to this guy. It's not a hard one. Yeah, but we're going to get the answer from a completely different source. We're going to get the answer from the residue theorem. Yeah? So if we want to do this from the residue theorem, then we're going to have to think about this as a contour integral, or part of a contour integral. So we're going to do the following thing. Or maybe not think of this, or transform this, or I'll think of transforming this into a contour integral. contour integrals over, well, we've learnt them over nice curves, right? So we don't want to do anything from 0 to infinity. We're going to do something from minus r to r as r gets bigger. And we're going to create a contour like this. So we're going to have minus r to r, and we're going to create a semicircle like this. Okay? That's the contour we're going to do, and that's called gamma of r. Yeah? So I hope gamma of r is clear and I don't have to explicitly define it. It's just this semicircle centered on 0. Yeah? So consider the contour integral gamma of r 1 over 1 plus z squared dz. Now, the part which is along the base of this guy here, this part is exactly part of the thing we want to understand, because when z is on the real numbers, then 1 over 1 plus z squared is 1 over 1 plus x squared. Yeah, that's exactly what we want. Yeah, so this is the thing we're actually interested in. Yeah, and it turns out that we don't have to care about the other part, particularly because if we look at the other part, so let's call this other part here. Well, actually, let's not bother. Let's just use the notation we have. So this thing can be broken down into the integral from minus r to r of 1 over 1 plus z squared dz plus the integral of the other part. The contour take away that part. And I claim that thing here we don't have to care about, because as r gets bigger and bigger, this thing will just vanish. And let's see why. So if we just create a parameterization, so let z of t be a parameterization of this part right here. So let's let it be r e to the it, where t goes from 0 up to pi. Then that's exactly this, giving this guy right here. So z prime of t is equal to I r to e to the it. So then this thing in the red box turns out to be integral from 0 to pi of 1 over 1 plus r squared e to the 2it, like this. And then the derivative, let's put it here, I r e to the it dt, right? So we can take the absolute value signs, right? And then this thing is less than the length of this thing. Well, now it's just an ordinary integral, so it's less than pi. And then let's put the absolute, actually let's do it since it's just now an ordinary integral. That's the integral from 0 to pi, and then we put the absolute value signs throughout this. So the absolute value signs, if we put the absolute value on the top, we just get r, right? If we put the absolute value on the bottom, then this expression here, as we arrange t from 0 to pi, it's always going to be less than 1 plus r squared. Because this is 1 plus a complex number. So this is the number 1, and then plus a complex number. Yeah, and the very worst thing it can be is if it's on the other side, right? So it can be here, it can be here, right? I mean, this is not a big point, because the 1 is insignificant compared to the r squared. But it nevertheless is the truth that we have this inequality. We just see from this geometry. Yeah, this is dt. So that's just equal to pi r over 1 plus r squared, and then this goes to 0 as r goes to infinity. So as r goes to infinity, we don't have to care about this part right here. So it does become just the integral over the base of this guy here. Yeah? Yeah? Okay, and what's cool is that this is now just an integral of a function over a closed curve. And it would be 0 unless we had some singularities inside the closed curve. So what do we see happening here? What singularities do we have going on here? Not quite. So let's try and factor z squared plus 1. How can we factor it? It's a complex polynomial, so we can definitely factor it. That's what we learned. So what are the factors? What are the factors? Yeah. Z minus I, Z plus I. Yeah? Cool. All right. So then this thing becomes this guy. Z minus I, Z plus I, dz. Okay, so what are the singularities inside our contour? I, yeah, sorry, I thought you said pi, yeah. I. So this is our only singularity inside our contour. The other one is on the other side, it's outside, yeah? Cool. All right, what is the nature of the singularity? What kind of singularity do we have? You might be muted, Annie. Unmute yourself. A pole. What kind of pole? A simple pole, yeah? It's a simple pole, yeah? Its blow up around I is just of order 1, right? Yeah? It's actually already in the form of 1 over z minus the point of the singularity times a holomorphic function. And this is nice holomorphic around the value I itself, yeah? So we have a simple pole at this thing, yeah? So what we need to do is just write 2 pi I, and then the residue at I of this function, let's write it like this, 1 over 1 plus z squared. That's the residue theorem. That's what it tells us. Yeah? There's only one thing, and the residue is easy to count. Well, the residue is easy to calculate because it's just a pole. The residue of this guy is the limit as z goes to I of z minus I of this function. And we write the function as z minus I, z plus I. And then these minus i's cancel, z minus i's cancel. So this is just the limit as z goes to I of just 1 over z plus I, which is just 1 over 2i, which is just minus I over 2. Yeah? Cool. So from this thing here, from star, we have that the answer should be 2 pi I times minus I over 2. So what's that? Minus I times I is just 1, so that's just equal to pi. So we think that for every single r, the integral of this, where is it? Where is my guy? Of this function is just equal to pi. That's what we think. Huh? Yeah? Cool. So how do we conclude the proof? Well, this is true for every single r, so we can take the limit as r goes to infinity. So pi is equal to the limit as r goes to infinity of the integral around gamma of r, 1 over 1 plus z squared dz. Yeah? And in the limit, when we break it up like this, then this part survives and this part vanishes. So this thing just turns out to be the integral from minus infinity to infinity of 1 over 1 plus x squared dx, which gives us the answer. Now let's see what calculus tells us. Let's see if mathematics is consistent. So let's do it like this. So this is an even function, so it's like this. So this is 2 times the limit as r goes to infinity. The antiderivative, as you people told me, is arctan. And sure enough, we know what arctan looks like, right? It looks like this. Horizontal asymptote at pi over 2 and minus pi over 2. So this thing is just 2 times pi over 2, which is just pi. And that is the right answer. Yeah? In this particular case, it's actually easier to use calculus than it is to use the residue formula. Huh? But this is just the beginning, because this now has enormous power. Now we have the ability to transform real integrals into contour integrals in some way, like such as this, taking the limit. And in all cases, we're going to do something like this. We'll have some contour where we expand it in some way so that the only parts we're interested in are just the real parts. and then we'll be able to extract out specific things, exact answers to real integrals that are inaccessible from real analysis techniques, which is absolutely extraordinary. So entering the complex world, proving these deep theorems about things in the complex world, things that don't exist in the real world, gives us information about the real world. This is a completely different way to calculate this quantity. This is completely different. These are in different parallel universes, these two answers. But we get the same answer. This stuff does give us this kind of thing. So imagine excitement back in the 18th, 19th century when they started to see this and realized they've been struggling for hundreds of years to explicitly calculate various integrals. And then this bunch of techniques comes along, and suddenly you can do it by just calculating the residue at various singularities of holomorphic functions that have poles at certain points inside contours. This was very hot stuff, cutting edge stuff, and it's still very hot stuff. It's still very, not in the sense of cutting edge stuff, but it's very neat. It's very impressive. It's very cute. And that's what we're going to be learning in the next class. We're going to practice this on other integrals, and then we'll learn more about the singularities of holomorphic functions. Okay, so that's it for today. Have a great day, and I will see you all on Friday. Bye-bye, people.